How do we go about finding the volume generated by this area under the curve, where this area is the area under the curve of y equals to fx from x equals to a to b? Now, to find the volume generated, we first need to know which axis is it rotated about. So suppose it is rotated about the x-axis. Now, in order for us to find the volume, there are two ways. Let me first introduce the this method. Now, so what the this method does is that first I will divide the area under the curve into many small strips. Okay, and all this small strip will have the same thickness, denoted by small change in x, and the reason for x is because it's the horizontal distance. Alright, and for all this little small strip, I'm going to pick one of them and ask myself if I am to rotate this strip that I've just shaded about the x-axis 360 degrees, what do I get? Now, you're going to get a this, okay, and the thickness of this is the same as the thickness of the strip, okay, and it is also not difficult to realize the radius of the circular disc is actually your y value. Alright, so the radius is y. Now, if I want to find the volume generated by this piece of shaded area, it is actually equivalent to me adding up the volume generated by each of these discs. That's why we call this the disc method, because basically we cut the area under the curve into different strips, and each of these strips being rotated about the x-axis 360 degrees will generate a disc. Summing up the volume of each of these discs is going to give me the area that I'm looking volume that I'm looking for. Okay, so the volume of one of these discs is just pi r square. So r square in this case is y square, and the thickness of the disc dx. Now, but this is only for one disc. I need many of it, so I will sum up all the discs. Now, this would not be accurate, right? If you look at the diagram, of course this is not like a disc. It seems to be something like an arc over here, not so much of a straight line. But if my small change in x is very small, means the thickness of the disc is so small, it's almost zero, then I could actually get a very good approximation. So I'm going to consider the limit of this thing when my small change in x is almost zero, and this is equivalent to integrating pi y square dx. And because we're looking at integration with respect to x, our limits is also the x value, so it will be from a to b, and this is what we know as the this method. Now, there's another method, okay, to find the volume, okay, generated by the shaded area. So in this method, we cut the shaded area or the area under the curve, okay, into strips like that, and each of these strips is actually perpendicular to the axis of rotation. Now, we can also cut the area under the curve into strips like that, okay, which are actually parallel to the axis of rotation. And in this case, each of these strips will also have the same thickness, and it is denoted by small change in y. Now, why is it small change in y? Because we're looking at like the vertical distance, alright, so denoted by small change in y. Now, let me show you how do we go about finding the formula for the shell method. Let me erase these drawings. Now, again, I'm going to pick one of the strips, and then I'm going to ask myself if this strip is going to be rotated about the x-axis 360 degree, what would I get? Now you're going to get a cylinder, but not a full cylinder, but rather a hollow cylinder. Okay, and this hollow cylinder actually came from this strip, okay, rotating about the x-axis 360 degree, which means the thickness of this hollow cylinder is actually small change in y, and it's also not difficult to see that the radius, okay, is actually from the y value, so it's y, whereas the height of the cylinder is u reading off the x value, and in this case this is the height, and suppose if this is x, then the height will be b minus x. Okay, now how do I actually find the volume of this hollow cylinder? Because in the shell method, okay, and why is it called shell? Because these hollow cylinders are known as shells. Okay, now to find the volume, I need to sum up the volume of all these shells. Okay, and so I need to find the volume of the shells. How do I go about doing it? Now what I can do is I can cut open this hollow cylinder or this shell and unroll it into a sheet. Now when I unroll it into a sheet, now this sheet will be of a certain thickness, and no price for guessing the thickness. Thickness is just small change in y, and this width here is your height of the cylinder. Now how about the length of this sheet? Now the length will come from you unrolling your cylinder, means this will be the circumference, which is 2 pi r, and in this case my r is y. Okay, so what's the volume of this sheet then? It's going to be 2 pi y times b minus x times the thickness of the sheet. Alright, so this is the volume of just one shell, and I need to sum up for all the shells. So I'll sum it up, and I'm looking at the limit of this sum when my thickness of the shell is actually almost 0. Okay, now you need the thickness to be as small as possible, as close to 0 as possible, in order to have a very accurate volume of revolution. Alright, that explains why there is a limit when small change in y tends to 0, and this is equivalent to saying you integrate 2 pi y b minus x dy. Alright, because we are doing a dy, then our limits will have to come from the y values, and in this case 0 to this point here will, if this curve is called y equals to fx, then this will be my fb. Okay, so to fb. Alright, now some of you will remember coming across in textbooks that the shell methods formula for volume looks like this. Integrate, 2 pi xy dy. Suppose if my rotation, my axis of rotation is actually x, and this is like my y values, okay, from y1 to y2, then you'll be wondering, then why is it different from that of this question? So now this is a very important point. Do not just memorize this formula without understanding. This is a general formula, and depending on the scenario, the x in this case is actually b minus x, which is actually the height of the shell or the hollow cylinder. So in order for you to apply the shell method, it is not about applying this formula, it's about you being able to dissect the area into many strips. See that when you pick one of the strip and rotate it about the axis of rotation, what is the shell that you get, and are you able to identify the dimensions of the shell, which allows you to identify the dimension of the unrolled shell, which is basically a strip, okay, or a big piece of a sheet, so that you are able to find the volume of this sheet. And when you sum it up and find the limit when change in y tends to 0, this is where you are able to find the formula of the shell method that is applicable to the question that you're trying to solve.